Video 9.7, Taylor Polynomials and Approximations. There are three different I can statements. I can find polynomial approximations of elementary functions and compare them with the elementary functions. I can find Taylor and Maclaurin polynomial approximations of elementary functions, and I can use the remainder of a Taylor polynomial. The third we will not be doing quite yet. That will be a few days from now. The whole objective of today's lesson is we are going to create a polynomial that approximates a function around a c-value. How I want to start the lesson is opening up a Desmos link. And what this represents is the function I'm dealing with here is e to the x. Let's scroll down. So the blue is e to the x. This is a graph about applying Taylor series onto a specific function. And what you're going to see is as the degree of the estimated function, noted a in Desmos, that's the degree, as that increases, the red graph here is going to get closer to the original graph centered at B. And again, here B in Desmos is the center. But before I start adjusting the degree, I want you to notice that when B is equal to 0, so in this case, x is equal to 0, the two functions, the function and the polynomial, I should say, are exactly the same. That's always going to be the case. But then as we move away from that center point, they're not the same at all. But if I adjust the degree, so from a degree of 1 up to a degree of 2, watch what happens. All of a sudden, the red graph becomes closer to the blue graph, not only at b equals 0, but at other places, other b values on the curve. And I'm going to increase the degree again. Degree 3, it evens closer. Degree 4, closer, all the way up to degree 5. Almost exactly on the polynomial. The red polynomial is almost exactly on the blue function, which basically says as the degree of our polynomial increases, it is a much better estimate of the actual function. So now I'm going to go back over here, and that's exactly what goes back to our objective. So you might be thinking, well, why are we doing this? Well, the nice thing about this lesson is the basic idea behind the lesson is that we like to create polynomials because they are easy and sometimes they're easier to take derivatives of and integrate quickly. So when we think about Taylor polynomials, we're really taking something that is hard and turning it into something that is easy. And so that is our purpose here. We're going to be today creating polynomials that are going to approximate a function. And like I said, they're going to be exactly the same around that c value. And they're going to be different as we move away from the c value. But the larger the degree of the polynomial, the more exact they will be. All right. So in my notes, we're not covering this screen or this one or this one. Since Miss Larson and I did the Desmos, we've changed the way we are approaching this lesson, and it is much better. So I'm going to jump all the way to this screen. Definitions of nth Taylor polynomial and nth Maclaurin polynomial. So here is how we're going to create these. If f, the function, has n derivatives at c, then the polynomial, and c in this case is the b value we used in Desmos, then the polynomial we create is going to look like this. N is the degree of the polynomial. And so based on that, that's going to tell us how many derivatives that we have to take. Because as you can see, if I'm creating an nth degree polynomial, I'm going to have to take n derivatives divided by n factorial times x minus c to the n. And like I said, c is what the polynomial is centered around, and they have to tell us what that is. Now, there is a special kind of Taylor polynomial, and it is a Maclaurin polynomial. If you are ever told that c is equal to 0, it is automatically called a Maclaurin. It's still a Taylor, but it's a special subset of the Taylor polynomials. So right here, I think I just pretty much said that. A Maclaurin series is a special type of a Taylor series. It is generated by f at x equals 0. C equals 0, x equals 0. That's what the polynomial is centered around. All Maclaurin series are Taylor, but not all Taylor are Maclaurin. So obviously at this point, since it's a video, you would stop the video and write down this formula, because this is the formula that we are going to be using to create these polynomials. Let's do an example. Find the Maclaurin polynomial of degree n for the function. Well, degree n is going to be 5 because I tell you that. I'm telling you it's a Maclaurin, so right away we know that, like we said, every Maclaurin is a Taylor, but in this case, C is 0. So the first thing I like to do when I'm creating these polynomials, I first just start taking derivatives because I know I have to take 5 derivatives. Like I said back here, based on the degree of your polynomial, that's going to tell us how many derivatives we have to take. So let's start by doing that. So we know f of x is e to the negative x, and I'm just going to start taking 5 derivatives. And when you get to the 4th derivative, you don't do 4 tick marks, you write a 4. And, oh, I gotta scroll. And the 5th, oh, shoot. And the 5th derivative. Okay. And now I'm going to evaluate all of those at 0, because in this case, c is 0. That's what we're going to plug in for x. So f of 1, f of 0 is 1. F prime of 0 is going to be negative 1. There we go. So we have all of that done. And so now we're ready to put it all together and create our polynomial. So we're creating a polynomial of degree 5. We have to start with that, the value of the function at 0. Then we take the first derivative at 0 times x plus the second derivative at 0 times x squared, remember, divided by 2 factorial. Again, we go back to that formula. Each time we're dividing it by n factorial. I didn't show it here because 1 factorial is just 1. All right, plus x to the third over 3 factorial. I'm going to have to go down here because I'm going to run out of room. Plus the fourth derivative. And x to the fifth over 5 factorial. All right. Well, we have all of that information above, so let's put it all together. We know the value of the function at 0 is 1. The value of the derivative at 0 is -1. So that's just going to be negative x. And here, the value of the second derivative at 0 is 1. Oops. So that's just going to be plus 1x squared over 2, because 2 factorial is just going to be 2. But I'm thinking, it doesn't make us simplify that. So I'm going to just leave it like that. And then the third derivative at 0, that's -1. So negative x cubed over 3 factorial plus x to the fourth over 4 factorial minus x to the fifth over 5 factorial. I'm just checking to make sure everything looks good. Yep. That is the 5th degree polynomial. The Maclaurin 5th degree polynomial that is going to be approximating the function f of x equals e to the negative x. As our degree gets bigger and bigger and bigger, it's going to exactly approximate that function. Example 4. We're going to find the Taylor polynomials. Oh yeah, this is a good one because it's not a Maclaurin, so it's different. Find the Taylor polynomials of degrees 0, 1, 2, 3, and 4 for f of x equals ln of x centered at c is equal to 1. Well, we know that we're going to have to find 4 derivatives because I need to find a 4th degree polynomial. So I might as well do that first. So our function is ln of x. So I take my first derivative. That's 1 over x. Oh, I know I did that. Okay. Which I'm going to write it like that because taking a derivative, it's much easier. So now the second derivative is just going to be negative x to the negative 2, which is obviously equivalent to -1 over x squared. And the third derivative is going to be 2x to the negative 3, which is the same thing as 2 over x to the third. And the fourth derivative is going to be -6x to the negative 4, which is equivalent to, scroll, -6 over x to the fourth. Now we're going to evaluate all of those, not at 0 like we did before, but at 1 because c is equal to 1. So that's what we're plugging in for x. So f of 1 is ln of 1, which is 0. And that's just going to be 1. That's going to be -1. It's It's going to be 2. And it's going to be negative 6. 1, negative 1, 2. There we go. All right, let's first create a polynomial of degree 0. Polynomial of degree 0 is only going to use the value of the function at 1, which is equal to 0. It's found right there. Polynomial of degree 1 is going to be f of 1 plus f prime of 1 times x minus our c, which is 1, all over 1 factorial, but we don't have to write that. It's kind of silly. I'm not going to write that. And if we plug that in, that is going to be f of 1 is 0 plus f prime of 1 is 1, and then which is just going to be obviously just x minus 1. And the polynomial of degree 2 is going to be f of 1 plus the first derivative plus the second derivative squared all over 2 factorial. All right. Just double checking this. That looks good. Which ends up being, well, we already know f of 1 is 0, and then f prime of 1 times x minus 1. We found that was x minus 1, so we can write that. The second derivative at 1 is negative 1, so that we'll just change that to a negative. So it's going to be negative 1 over 2 factorial times x minus 1 squared. All right, third degree is going to be, and I'm doing a bunch of these just so that you start to feel comfortable with this. And plus, oh, you know what? That's not going to let me write over there. I'm going to have to write down here. Third derivative, x minus 1 to the third over 3 factorial. Okay, so we're going to grab all of this, which is x minus 1 over 2 factorial, x minus 1 squared. And technically, I probably should put that in parentheses like I did the other ones. I should fix that. Plus the third derivative at 1, which is 2 over 3 factorial, x minus 1 to the third. And we have one more, our fourth degree. So again, that is going to be 1 plus f prime of 1, x minus 1. That is a prime plus second derivative over 2 factorial, x minus 1 squared. Scroll down here, the third derivative. minus 1 to the 4th. All right. So we have x minus 1, 2 factorial x minus 1 squared plus 2 over 3 factorial x minus 1 to the 3rd, which look what that's grabbing. That's really just grabbing the polynomial of degree 3. That's all that is, if you can see the pattern as we've gone. And now I'm adding on the final term of that polynomial, which is this. And that is going to be negative 6. So we don't need a plus because it's going to be a minus. So we have negative 6 over 4 factorial x minus 1 to the 4th. And as we do more examples, we're not going to ask you to find all of these different polynomials of different degrees. We would just say, find the polynomial of degree 4. I wanted to do this to show you that there's a pattern as you go from one polynomial to the next. And again, the polynomial and the function are exactly the same at c equals 1. But as we go further away from that, they're different. However, as our degree of our polynomial gets larger, then the polynomial approximates the function very closely everywhere, not just at that c value. All right. And here's a little graph. I want to just kind of go over this with you. So in these pictures, we have a polynomial of degree 1, degree 2, degree 3, and degree 4. The function that we're using here is our ln of x that we just did. And we're going around c equals 1 or x equals 1. And notice, just like I just said a little bit ago, the graphs are pretty much identical, all of them, at x equals 1. Notice that. But as we get away from that c value, which is called our x value, they become more different. The polynomial does not approximate the function very well. But as you can see, as the degree gets bigger, it is more closely approximating the function. And here's a little example, which I will be doing more of these examples on Friday. For instance, the 4th degree polynomial at 0.9 is approximately equal to this value. And when we ln, use the function, and we plug in 0.9 as an x value, you're also going to get negative 0.105361, which is, look at how very close they are. This would not happen if we use the polynomial of degree 1. These values would be much more different. So what we're going to do, we are going to pause right now. And what we will start with on Friday is we're going to find the Maclaurin series, but we're only going to find a polynomial, this polynomial of degree 6. So if you want to pause the video and try that, and then I will pick that up with you on Friday. But I'm going to show you, make sure we're not doing any of these. We're only going to find the polynomial of degree 6 for this function, and then we're going to use that polynomial to approximate the value of cosine of 0.1.